Okay, so let's have a look at public key encryption. For this, we'll have a look at some of the basics of what public key encryption actually does. Later on in the module, we'll be looking at the applications of public key encryption into key exchange and also into digital signatures, along with looking at digital certificates. So for this, we'll have a look at some of the basics around public key encryption, and then we'll look at mainly RSA and elliptic curve, and also touch base with LGAMO public key encryption. And then finally, we'll look at how we would store our keys within a key management system. Okay, so let's look at some of the basics. So what we have really is that we generate a special key pair. So this is a mathematical operation between the two keys. So what can happen is that if we encrypt with one key, then it is the other key that can then decrypt. Doesn't matter which one or the other, we can encrypt and then decrypt with the other one. So it's not like symmetric key encryption where we only have one key. In this case, Alice will generate a key pair. We define one of the keys as a public key and the other one as a private key. The public key should be the public key can be distributed to anyone who wants to communicate with Alice. But the private key is kept secret. So we must make sure that Alice does not share her private key with anyone else, but can share her public key openly. So the public key is a little bit like a padlock. Alice could distribute her padlocks to whoever she wanted, and then they could lock a box for her, and then only she will have the secret key which will open the padlocks. So the main methods that we have to be able to apply our public key encryption is to use it for encryption. And in this case, Bob wants to send Alice a secret message. So Alice sends her public key to Bob. We'll cover how that happens because obviously we need to make sure that Eve hasn't sent the wrong key. But let's say that Alice can get the trusted public key to Bob. Bob then encrypts the data with Alice's public key. He then sends it over, and the only key that can now decrypt the data is the private key. So in this way, the key pairs work together to be able to encrypt and then decrypt. So this is similar to what we found with symmetric key. Unfortunately, public key isn't very efficient when it comes to large amounts of data. So often we're encrypting a small amount of data, where symmetric key is used where we have larger amounts. The second method that we have is when we want to prove the identity. And in this case, Alice signs the data. She takes a hash of the data and then signs that with her private key. She then sends the data over, and Bob checks the signature with her public key. So again, Alice will distribute her public key to Bob, and Bob will prove that she signed the data. So this is known as a signature. And the third method is where we want to share a key. So let's say that Bob has created a shared key that he wants to use. Now, when Bob connects to Alice will send over her public key. That can then encrypt the shared key and be sent over. Now, Alice will use her private key to be able to decrypt the key, and they both have the same key. This is known as key exchange. And it's used or it has been used in TLS. Unfortunately, it's not a secure method, as the leak of the private key could cause earlier keys to be compromised. But these are the three main areas that we would implement our public key encryption. Okay, so here's the first one. Alice sends over her private key, and then Bob encrypts into ciphertext. She then uses her private key to be able to decrypt the data back into plain text. We can also use it in terms of signing. So in this case, Bob is going to sign a message. So he takes a hash of the message, and then he uses his private key and typically creates a nonce value or a random value, and then creates a signature. The signature is often known as R and S. That is the digital signature. Then Alice uses Bob's public key to verify the signature by also taking a hash of the message. If the signature is valid, then she knows that Bob signed the message with his private key. Typical methods that we have here are ECDSA, which is used in Bitcoin and Ethereum. That uses elliptic curve key pairs. EDDSA, that also uses elliptic curves. RSA and DSA. This uses discrete log methods. This one uses the RSA encryption method, and as I said, these two use elliptic curve methods. And this shows the key exchange. So in this case, Bob is creating a key. He then encrypts that with Alice's public key, sends it over, and then she will use her private key to be able to discover the key that Bob wants to use. Bob and Alice can now create a tunnel between them using this secret key. This will be a symmetric key. So the main methods that we use for public key encryption, or the main difficulties, are with integer factorization. So as we'll find, we create two prime numbers, p and q, and we create a public modulus called n. The difficulty here is to be able to factorize n into p and q, given that we have large prime numbers. Then we have discrete log methods, and with this we have the form g to the power of x mod p. And then elliptic curve methods we'll cover, but these are used extensively these days in smart cards, IoT, Tor, the Tor routing, and in Bitcoin. And so the strength that we have for our public key encryption methods means that we need to have a certain strength to be able to make sure that our method can't be cracked. So in this case, for RSA, the public modulus needs to be at least 1130 bits long. Typically we look at 2K or 4K sizes of RSA modulus. But it's important that we understand the strength of each of the methods. So here are the three main methods that we have: RSA, Elgamal, and elliptic curve cryptography. With RSA, we take two prime numbers and we calculate a public modulus. We then compute a value of phi, which is p minus 1 times q minus 1. We pick a value of e that doesn't share any factors with phi. And then we do an inverse mod of e mod phi. I'll explain that in a little minute. We then end up with a public key and a private key. The public key is e and n, and the private key is D into M. When we cipher, we take the message and we raise it to the power of E mod N, and then when we want to decipher, we take the cipher and raise it to the power of D mod N, and it should work. An extremely powerful method for creating digital signatures is elliptic curve cryptography. As these keys have increased to be quite large, then elliptic curve methods are often much more efficient and typically use 256-bit private keys rather than the bigger 2 to 4K keys here. For this, we have a curve which is defined with its x and y by this type of equation here. Y squared is equal to x cubed plus a, x plus b mod p. As we'll find, we have a secret key or a private key, sk, and we have a public key. What we have then is a base point on the curve, which will then be used to be able to compute the public key. And the final method is LGAML, which isn't really used that much, and it's G, a generator value to the power of x mod p. We end up with a public key and a private key of those values. Okay, so first we'll look at RSA. And RSA was created by Vest, Shamir and Edelman, and they created the RSA method around 1977. For this, we take two prime numbers, P and Q. We then work out that N is equal to P times Q. So if I took 3 and 11, then it's obvious that the modulus, or N, is 33. 3 times 11. We then work out phi, and phi is P minus 1 times Q minus 1, so that's 2 times 10, so we get 20. We then select a value of E that doesn't share any factors with phi. So the factors of phi are 2, 4, 5, 6, and so on. So let's select 3 because that isn't one of the factors of phi. So our encryption key is now 3 and 33. We must now find a value of D when multiplied by E, and we take mod 20 gives a value of 1. It's called an inverse of E mod phi. So in this case we could try different values of D, and we can see that when D is 7, we get 7 times 3 mod 20, and that will equal 1, so that works. So our decryption key is 7, 33. Okay, so there's our encryption key and our decryption key. So now let's try to cipher. We'll take a message. Message is 5, say. Then we raise it to the power of 3, which is our E value. Then take mod of our public modulus 33, and we get 26. So we'll take our cipher, raise it to the power of D, which is 7, mod N, and hopefully we get back the value of 5, which was our original message. Okay, so here's a simple calculator. So there's P and Q. We can work out N. There's phi. So we'll work out a value of E here to be 5. We can then pick the inverse of E mod phi, and we get 77. This is the public key and the private key. We can then go ahead and take a message, and hopefully when we take a message of 32, we encrypt to get 2, and then we can return back here. Okay, so this shows examples of larger keys here. The value that you see here, 010001, is actually 65,537. That's the typical value that we use for E. So let me show you just some simple Python to be able to implement this. Okay, so we'll try to do 12 lines of Python. Okay, so in this case we'll generate our prime numbers of a certain size. So we could take 512-bit ones, but we'll take a smaller one of 80. When we multiply them together, in this case we get this value, and we pick our E value typically to be 65,537, and then we work out D here. So D is the inverse of E mod phi. Here's the cipher, and then we can decipher here. So let's look at the code that we have here. And this is the inverse mod here. We can see here that we compute phi, which is p minus 1 times q minus 1. This is the value of E. So we compute the inverse of E mod phi to get D. We can then easily, and we typically use the POW function because it's much more efficient than using double star E. So we take the message, we convert our strings into an integer value, and then we take m to the power of E mod n, and then to decipher we take the cipher to the power of D mod n, and it should all work out. Okay, so there we go. We'll try an even larger one, and hopefully it should all decipher perfectly in the end. Get our message back there in the end. Okay, so what does the key actually look like? Well, we can generate the key with OpenSSL, and this is the command that we can actually use. When we show it, we can actually see the component parts of it. This is a 1024-bit key, and this is the public modulus n. We can see here's the value of E, and there is the value of D. The prime number is here, and the other prime number is there. When we multiply these two values together, we should get that one. So you can see there that this is twice as long as these. So we'll take two 512-bit keys together and multiply them. Okay, so there's the component parts. There's the P and the Q and the N and the E and the D. And this gives us our key. And we need a form to be able to save it in, and we all often use the PEM format to be able to define our key in a base64 format. But this really contains all this information here. Along with this, when we have cipher messages, we might want to paste them into an email. So we'll get the format of the encrypted message put into what's called an ARMOR format. In this case, we have a header and a footer for the encrypted message. So the way that we would run this if we were sending secure email, say, or communicating with lots of systems, is that Bob would add Alice's public key onto his keyring. So we can see the public key is here, but he would also have his own private key there. So anything that was destined for Alice, then rather than having to request Alice's public key each time, he would store the trusted public key on his keyring. Then when he was sending email and he wanted to digitally sign, he would actually sign it with his private key from his keyring. So now let's look at elliptic curve cryptography, or ECC. And this is a very important area and is used extensively in digital signing. Applications include Bitcoin, Ethereum, IoT devices, and so on. And the two main signature methods are ECDSA and EDDSA. The basic equation that we have is y squared is equal to x cubed plus ax plus b, where a and b are constant values for our curve. If we were to plot that in an analog form, we'd get something in the form such as this. So what basically happens is that we define a base point on the curve g. That's an x and a y base point. We then have a secret key, which is a scalar value, just a multiplier. And then from that we get a public key, which is another point on the curve. Because when we add 2 points together, then we always get a point in the curve with an elliptic curve. So SK is the secret key and PK is the public key. And there are two basic operations in here, point add and point multiply. And this is a very efficient operation where we add points. So basically, if we have 5g, it basically means g plus g plus g plus g plus g. And we can add the point g 5 times. Okay, so as I said, we pick our point on the curve, and that's our base point, a g. We then generate a random value, and this becomes our private key, and our public key becomes n times g mod p. Typically, the private key is 256 bits, and our public key is an xy point, so will be 512 bits. As I said, Bitcoin is used with elliptic curve, and we would use this curve here for Bitcoin and Ethereum. Other curves have been defined by NIST, and an equivalent curve to SEPT 256K1 is NIST 256P256. The Tor network uses a different curve, and it uses curve 25519. If you're interested, then because we're bringing in the mod operation of a prime number, we don't actually get this continuous curve. What we get is a number of points that are mapped onto x and y. So we might take a point and add that point to itself and get another point, and so on. So the points that we get, we should be able to keep multiplying our points and still find another point on the curve. Okay, so this is used, elliptic curve is used in Bitcoin generation, and this is your private key here. We then take a hash of the public key. We then take a digital signature of the public key with the ECDSA signature method, take a hash of that, and then we can actually create the public address of the Bitcoin wallet. We'll be covering this in more detail in a later unit. So with a Bitcoin transaction, Bob will get Alice's public address, add on the transaction, then with his private key, he will then sign the transaction with an ECDSA signature to be able to prove that he signed off the signature. Anyone with Bob's associated public key will be able to prove that transaction. Okay, so this is the signing process here. We have a hash, we apply a private key, and then the public key is then used to be able to prove the signature. But how do we get Bob's public key to Alice in a trusted form? Well, for this we need Trent, and as we'll find, the PKI infrastructure allows us to be able to implement this trust infrastructure where Trent can actually sign for the public key of Bob. So here is an example format for a key. So we have the basic parameters of the curve, and then we have the private key in here. When we expand that, we can see that this private key contains, there's the private scalar value, and there is the public key point. In this case, we're using the curve sept 256K1. So if the parameters are known for that curve, then it's possible for us to be able to match that public key and private key. Okay, so here's one here. There's another example with the private key and the public key. But this time, let's look at the parameters within the curve. So this is the prime number that's used. This is the value of A, B, and here is the generator. The order is actually the number of points that we can have on the curve, because not all points are actually possible. But this is the G generator point here, and it's defined for the curve that we're going to use. There's the A value and the B value that we saw before when we had our equation of this. Okay, there's the prime number here, there's the value of A, and there's the value of B. And we're taking the generator point as the base point of which we're going to compute. So if we take a secret key of SK, then we multiply that with the base point to get the public key. And basically that's just G added SK times, keep adding. But as I said, it's a very efficient operation within elliptic curves. So we'll be covering key exchange later on in the module, but one of the applications here for elliptic curve is within elliptic curve Diffie-Hellman, which is a key exchange method, and it's used in the Tor network. So in this case, what we have is a key pair for each node in the Tor root, and then using key exchange or elliptic curve Diffie-Hellman, then Bob can negotiate a key for this node, a key for this node, and a key for this node. So this is a symmetric key, such as AES. So the way that Tor will work is that Bob will encrypt with the red key, then encrypt with the green key, and then encrypt with the purple key. He sends that along, and then the purple key is extracted, so we get this, and then will be passed on to here. This node will then take this key and decrypt to take the green key off, and then finally we'll just have the red key, which is encrypted and then can be decrypted here. Okay, so this is an application of elliptic curve cryptography to do the key exchange method, and we'll be covering that in the next unit. So here are elliptic curve methods. There are typically 3 core curves that we use. Curve 25519, and that's used for the ED 25519 signature, and also used in X25519 key exchange. The SEPT 256K1 is used in Bitcoin, and that is used with the ECDSA signature method, and also within elliptic curve Diffie-Hellman for key exchange. And the NIST defined P256 is often used in the elliptic curve Diffie-Hellman method for key exchange. We can get larger curves and more secure ones, such as P521 and curve 448. And that leads into these signature and key exchange methods. Okay, so just touch base a little bit with LGAML. We don't really use it that much these days for public key encryption, but basically we take a generator and we raise it to a power X, and X is the private key. That then produces a public key, which is G to the power of X mod P. When we look at the Diffie-Hellman method in the next unit, we'll be able to see how this is constructed. Now let's look at how the methods of encryption and signing can actually work together. So an example is with pretty good privacy. So in this case, Bob takes a message that he wants to send to Alice. He then takes a hash of the message and creates a signature using his private key. Next, he'll generate a new symmetric key and then encrypt the message and the signature together. He then takes Alice's public key and encrypts the new symmetric key, and then that can then be sent to Alice. So Alice has used her public key, or Bob has used Alice's public key to be able to encrypt the symmetric key, which is used to encrypt the message and the signature. Bob used his private key to be able to sign the message. Now when she receives the message, she will then use her private key to be able to decrypt the symmetric key, which is used to encrypt the message. When she does that, she can then reveal the message and the signature. Next, she takes the signature and Bob's public key and checks the signature to see that it matches with Bob's public key. If it does, then she knows that Bob has signed the message, so she knows the message came from Bob. She also knows the credibility, the integrity of the message, because the signatures tie up, and also she knows that no one has read the message because only she can have the private key to reveal the symmetric key. Okay, so finally we'll look at how we manage our keys. So with this, we can use the KMS, or the key management system, in AWS, and this is us creating a key here. When we do that, we can create our public key or asymmetric key, and we either create keys for encryption, such as for RSA, or we could use signing keys. When we use signing keys, we can use RSA or our elliptic curve methods here. But when we're encrypting, we typically just use RSA methods here. Okay, so we select our key type, and then we can actually view our public key. So the public key can be viewable, and we can also download our public key as required. So that key, or the private key, is stored in what's called an HSM. So the HSM will secure the private key, and we can have the public key here. So whenever we need to sign or encrypt, we can actually sign it within our HSM or hardware security module. The standard HSM in a cloud infrastructure is typically multi-tenanted, where others can share the HSM, but obviously the keys are kept separate from each other. For highly secure applications, we can use our own cloud HSM, which will be a private space for us to store our keys. And this way, no one can get access to our private keys and the symmetric keys that we store. But obviously, this is much more expensive than using a multi-tenanted approach. Okay, so that's been a coverage of public key encryption. We'll go on to look at how we can use the elliptic curve Diffie-Hellman method and how we can create digital signatures and also store the public key in a trusted way. Okay, thank you.